Let's solve the equation tan 2x 5 degrees equals 1, where 0 degrees less than or equal to x less than or equal to 180 degrees. Let's start by recalling some key facts about the tangent function. First, tangent equals 1 at 45 degrees, and the tangent function has a period of 180 degrees. Let's visualize this on a graph. Here's our coordinate system, and here's what the tangent function looks like. Since we know that tangent equals 1 at 45 degrees, we can write 2x 5 degrees equals 45 degrees plus k asterisk 180 degrees, where k is some integer. Let's solve this equation for x. First, add 5 degrees to both sides. Then divide everything by 2. Now, let's find the values of k that give us x values between 0 degrees and 180 degrees. When k equals 0, x equals 25 degrees. Let's plot this point. When k equals 1, x equals 115 degrees. Here's our second solution. When k equals 2, x would be 205 degrees, but this is outside our domain of 0 degrees to 180 degrees. Therefore, our final solution is x equals 25 degrees, or 115 degrees. To verify these solutions, you can plug them back into the original equation. Both values of x will give you tan 2x 5 degrees equals 1. Let's solve this exponential equation step by step. We start with 3 times 9 to the x plus 5 times 3 to the x minus 2 equals 0. The first key insight is that 9 is actually 3 squared. So 9 to the x can be rewritten as 3 squared to the x, which equals 3 to the 2x. Let's substitute this back into our original equation. This gives us 3 times 3 to the 2x plus 5 times 3 to the x minus 2 equals 0. To simplify this, let's make a substitution. Let y equal 3 to the x. Then 3 to the 2x becomes y squared. This transforms our equation into 3, y squared plus 5y minus 2 equals 0. This is now a quadratic equation in terms of y. We can solve this using the quadratic formula. The quadratic formula states that y equals negative b plus or minus the square root of b squared minus 4 ac all over 2a. Here, a equals 3, b equals 5, and c equals negative 2. Plugging these values into the quadratic formula, we get y equals negative 5 plus or minus the square root of 25 plus 24 all over 6. This simplifies to negative 5 plus or minus 7 over 6. This gives us two solutions, y equals 2 over 6 or 1/3, and y equals negative 12 over 6 or negative 2. Remember that y equals 3 to the x. Since 3 to any power cannot be negative, we can only use the positive solution, y equals 1/3. Therefore, 3 to the x equals 1/3, which means x equals negative 1. Let's verify our solution by plugging x equals negative 1 back into the original equation. When we do this, we get 3 times 9 to the negative 1, plus 5 times 3 to the negative 1, minus 2. This equals 3 times 1/9 plus 5 times 1/3, minus 2, which equals 0, confirming our solution. Therefore, the solution to our equation is x equals negative 1. Let's solve a probability problem about birds nesting in spring and summer seasons. We'll use a probability tree diagram to help us visualize and solve this. Here's our tree diagram. In spring, a bird can either nest with probability k or not nest with probability 1 minus k. Then in summer, if the bird nested in spring, it can nest again with probability k over 2 or not nest with probability 1 minus k over 2. Similarly, if it didn't nest in spring, it can nest in summer with probability k over 2 or not nest with probability 1 minus k over 2. Now, we're told that the probability of not nesting in either season is 5 nights. This means that the probability of taking this bottom path, not nesting in spring and not nesting in summer, equals 5 nights. Let's expand this equation. When we multiply these terms, we get 1 minus k over 2 minus k plus k squared over 2 equals 5 nights. Multiplying both sides by 18 to eliminate fractions and rearranging, we get our quadratic equation. 9k squared minus 27k plus 8 equals 0. Using the quadratic formula, we get two solutions, k equals 1/3 and k equals 8/3. Since k represents a probability, it must be between 0 and 1. Therefore, k equals 1/3 is our only valid solution. Let's verify our answer. When k equals 1/3, the probability of not nesting in spring is 2/3, and the probability of not nesting in summer is 5/6. Multiplying these gives us 5/9, which matches our original condition. Let's solve this probability problem about apples. A farmer grows two types of apples, eating apples and cooking apples. Their weights follow normal distributions with different means and standard deviations. Let's visualize these distributions. The blue curve represents eating apples centered at 100 grams with a standard deviation of 20 grams. And the red curve represents cooking apples centered at 140 grams with a standard deviation of 40 grams. For part A, we need to find the percentage of eating apples that weigh more than 140 grams. This is the area under the blue curve to the right of 140 grams. To find this, we calculate the z-score, 140 minus 100 divided by 20, which equals 2. Using the standard normal distribution table, we find that the probability of a z-score greater than 2 is about 0.0228, or 2.28%. For part B, we need to find the probability that an apple weighing more than 140 grams is an eating apple. We know that 80% of all apples are eating apples. Let's look at both distributions above 140 grams. For cooking apples, the cutoff of 140 grams is exactly at their mean, so 50% of cooking apples are above this weight. Given that 20% of all apples are cooking apples, 10% of all apples are cooking apples above 140 grams. For eating apples, we found that 2.28% are above 140 grams. Since 80% of all apples are eating apples, 1.824% of all apples are eating apples above 140 grams. Therefore, the probability that a randomly selected apple weighing more than 140 grams is an eating apple is 1.824% divided by 11.824%, which simplifies to 19 over 123. So the probability is 19 over 123 that a randomly selected apple from the container is an eating apple. Let's solve this complex problem involving polynomial roots step by step. We'll break it down into three main parts. Let's start with part A. We have a function g of x equals 2x cubed minus 7x squared plus dx minus e, where d and e are real numbers. Alpha, beta, and gamma are the three real roots of this equation. To find alpha plus beta plus gamma, we can use Vieta's formulas. For a cubic equation, the sum of roots equals the negative of the coefficient of x squared divided by the coefficient of x cubed. Moving on to part B, we have a new function h of z equals 2z to the 5th minus 11z to the 4th plus rz cubed plus sc squared plus tz minus 20. We're told that z equals p plus 3, I is a root. Since this is a polynomial with real coefficients, if a complex number is a root, its conjugate must also be a root. Using Vieta's formulas again, we know that the sum of all roots equals negative coefficient of z to the 4th over coefficient of z to the 5th. We can substitute what we know. Alpha plus beta plus gamma plus p plus 3i plus p minus 3i equals 11 halves. Since we know alpha plus beta plus gamma equals 7 halves, we can solve for p. For part C, we're given additional information. First, h of 1/2 equals 0. Second, alpha and beta are positive integers with alpha less than beta, and gamma is rational. Since 1/2 is a root, and we know p plus 3i and p minus 3i are roots, we only need to find alpha and beta. Since alpha and beta are positive integers, and their product must be a factor of 20, the constant term, and alpha is less than beta, the only possible values are alpha equals 1 and beta equals 2. We can verify this satisfies all our conditions. In conclusion, we've found that The sum of the roots alpha plus beta plus gamma equals 7/2 p equals 1, and alpha equals 1, and beta equals 2. Welcome! Today, we'll solve a challenging limit problem using L'Hopital's rule. Let's look at our limit. The limit as x approaches 0 of secant to the fourth power x minus cosine squared x, all divided by x to the fourth minus x squared. First, let's try to evaluate this limit by direct substitution. When we plug in x equals 0, we get secant to the fourth of 0 minus cosine squared of 0 in the numerator, which is 1 minus 1, over 0 to the fourth minus 0 squared in the denominator, which is 0 minus 0. This gives us 0 over 0, which is an indeterminate form. When we encounter an indeterminate form, we can apply L'Hopital's rule. This rule states that the limit of a quotient equals the limit of the quotient of the derivatives, as long as we have an indeterminate form. Let's find the derivatives. For the numerator, we get 4 secant cubed x times secant x tangent x plus sine of 2x. For the denominator, we get 4x cubed minus 2x. Let's try to evaluate this new limit. When we substitute x equals 0, we get 0 over 0 again. This means we need to apply L'Hopital's rule a second time, taking the derivatives again. The numerator becomes 4 secant to the sixth x plus 16 secant cubed x tangent cubed x plus 2 cosine of 2x. The denominator becomes 12x squared minus 2. Now, let's evaluate this limit as x approaches 0. When x is 0, secant of 0 is 1, tangent of 0 is 0, and cosine of 0 is 1. So our numerator becomes 4 plus 0 plus 2, which is 6. The denominator becomes negative 2. Therefore, our final answer is negative 3. Let's review what we did. First, we found an indeterminate form 0 over 0. Then we applied L'Hopital's rule twice. And finally, we evaluated the limit to get negative 3. Let's solve this field trip grouping problem step by step. A teacher needs to divide n students into 2 groups with exactly 3 students in the first group and at least 3 in the second group. For part A, we need to find an expression for the total number of ways to assign the students. Let's visualize this with some students. We need to choose exactly 3 students for the first group from the total n students. This is a combination problem. We're selecting 3 students from n students, where the order doesn't matter. The formula for this is n choose 3 or C, n3. Now for part B, 2 students ask not to be in the same group. Let's highlight these 2 students in red. There are 2 possible cases. Either student 1 is in the first group and student 2 is in the second group, or student 2 is in the first group and student 1 is in the second group. For each case, we need to choose 2 more students from the remaining n-2 students to complete the first group. This gives us n-2 choose 2 ways for each case. We're told this new number is half of the original number of ways. So we can write 2 times n-2 choose 2 equals 1/2 times n choose 3. Let's solve this equation. First, let's expand the combinations. After multiplying and simplifying, we get a quadratic equation, n squared minus 13n plus 36 equals 0. Using the quadratic formula, we get n equals 9, or n equals 4. Since we need at least 3 students in each group, n must be at least 6. Therefore, n equals 9 is our answer. Let's verify this makes sense. With 9 students, we'll have exactly 3 in the first group and 6 in the second group, satisfying our original conditions. Let's solve this problem involving arithmetic and geometric sequences step by step. We'll start with part A. For part A, we need to show that 2p minus q equals for the arithmetic sequence A, P, Q. Let's write out what we know about arithmetic sequences. In an arithmetic sequence, each term differs from the previous term by a constant difference d. Let's solve this step by step. First, Let's multiply the equation p equals a plus d by 2. This gives us 2p equals 2 a plus 2d. Now, we can subtract q, which is a plus 2d, from both sides. This gives us 2p minus q equals 2 a plus 2d minus a minus 2d, which simplifies to a. Moving on to part b, we need to show that s squared equals a t for the geometric sequence AST. In a geometric sequence, each term is multiplied by a constant ratio r to get the next term. Let's solve this. We can square s, which is ar, to get s squared equals a squared r squared. Then we can substitute t equals a r squared to show that s squared equals at. For part d, let's write out the first 4 terms of both sequences when it equals 9. For the arithmetic sequence, we can find p equals 5 using the fact that it's the average of a and q. Then the sequence is 9, 5, 1, negative 3. For the geometric sequence, we can find s equals 3 using s squared equals at. The sequence is 9, 3, 1, and 1/3. Finally, for part e, we have a new arithmetic sequence, u underscore n. The first 3 terms are given as u underscore 1 equals 9, plus lane 9, u underscore 2 equals 5, plus lane 3, and u underscore 3 equals 1, plus lane 1. The common difference is negative 4 minus 2 ln 3, which we can find by subtracting consecutive terms. To find the sum of the first 10 terms, we can use the arithmetic sequence sum formula. After substituting and simplifying, we get negative 90 minus 25 ln 3. Let's solve this complex problem involving parallel and perpendicular planes. We'll break it down step by step. Let's start with plane pi 1. It has the equation 2x plus 6y minus 2z equals 5. We're given point A with coordinates 2, 1/2, and 1. Let's verify that point A lies on plane pi 1 by substituting its coordinates. When we plug in x equals 2, y equals 1/2, and z equals 1, we get 2 times 2 plus 6 times 1/2 minus 2 times 1 equals 5. For part B, we're given plane pi 2 with this equation. When p equals negative 6, pi 2 is perpendicular to pi 1. For planes to be perpendicular, their normal vectors must be perpendicular. For perpendicular vectors, their dot product must equal 0. Let's set up this equation. When we solve this quadratic equation, we get k equals negative 3. For part C, we're now told that pi 2 is parallel to pi 1 with k equals 3. For parallel planes, their normal vectors must be scalar multiples of each other. This gives us p equals negative 3. For part D, we need to find point B, where the perpendicular line through a meets pi 2. The direction vector of this line is parallel to the normal vector of pi 1. Using parametric equations and substituting into pi 2's equation, we can find point B. The perpendicular distance between the planes can be found using the distance formula. When we calculate this, we get root 11. Finally, for part E, we can find pi 3 by using the same normal vector as pi 1, but with a different constant term to achieve the same perpendicular distance. And there we have it. We've found all the relationships between these parallel and perpendicular planes, determined intersection points, and calculated distances between them. The key was understanding the relationships between normal vectors and using them to solve each part systematically. Welcome. Today we'll work through a complex calculus problem involving derivatives, Maclaurin series, and approximations. Let's start with part A. We have the function f of x equals 1 minus x to the negative 1/2 power, where x is less than 1 and is not 0. We need to prove by induction that the nth derivative has this form. Let's start with the base case, where n equals 1. Taking the first derivative using the chain rule, we get over 2 times 1 minus x to the negative 3/2 power. This matches our formula when we plug in n equals 1. Let's verify. The a to the first power times 1 factorial divided by 2 to the first power times 0 factorial. times 1 minus x to the negative 3/2 power. Now for the inductive step, we assume the formula is true for n equals k, and we'll prove it's true for k plus 1. We differentiate the kth derivative to get the k plus first derivative. Moving on to part B, we need to find the Maclaurin series up to the x squared term. Using our formula from part A and evaluating at x equals 0, we get 1 plus 1/2 x plus 3/8 a squared x squared. For part C through E, we'll use this series too. First, show that the product of two such series gives us the stated approximation. Then, determine the convergence interval, which is x less than 1/4. And finally, use x equals 1/10 to approximate the square root of 3, which gives us 279 over 200. And that completes our solution. We used induction to prove the derivative formula, found the Maclaurin series, and used it to make approximations.